Okay, yeah, so this is pretty much just canceling out to 0 here. So that's what you needed to show that it's in the kernel. Make sense? Okay, let's do, I'll do part E of problem 6. And then be just a few things left that I haven't really done. I've done almost everything on the sheet. I really didn't think I was going to get that far into the sheet tonight, but I've actually managed to do most of it. And it's not even quite 9:30 yet, so ahead of schedule for me. Okay. This is great. You guys are going to be able to focus on your own studying now. You'll have seen enough of my examples. So let's do 6E on the review sheet next. It just wants you to solve the following differential equation, or determine the general solution, basically. D squared times the quantity D minus 1 times D squared plus 4 squared of y equals 11 e to the x minus the sine of 2x. Okay. Let's see if we can get this one to work. All right. What method are we going to use here?
Annihilators.
Annihilator method. And how do I know that? If, let's say, I just caught this problem out of the blue, how do I know that's the method we're going to use?
All the derivatives that you have to take. Oh, but also because you could annihilate the right side.
I do know how to annihilate the right side. Why can't I use variation of parameters, though?
Does it have to be for the second order?
Right. We only use variation of parameters. I only taught it to you for second order equations. So this is higher order, and you know how to annihilate the right hand side. You better be using that method, okay? So let's see if we can work it out. So the first step is to do what again? Step 1?
Auxiliary.
The auxiliary equation. What is the auxiliary equation? Can we write it down?
Yeah, r squared,
Mm-hmm.
r minus 1,
Okay.
r squared plus 4 squared is equal to 0.
Okay, r squared times r minus 1 times r squared plus 4, quantity squared. See, I was nice to you here because I gave it basically in factored form for you. You didn't, otherwise, I mean, this is a fairly big polynomial otherwise to find the roots. So this is how I'm going to get around making you factor, like, whatever this is, a 7th degree polynomial. I might give it to you in that factored form. Okay, so we need the roots of this, right? Including repeats and complex numbers and everything. So can somebody read them off for me?
It's 0, 0,
0 and 0.
1,
1.
and this one will be like plus or minus 2i,
Plus and minus 2i.
and plus or minus 2i.
And plus and minus 2i again. Be sure to write down all the repeats, everything that you have. Okay. Looks good to me. Once I have all the roots, what do I do next? We can write down the complementary function. Exactly. So let's do that. You want to tell me what it is?
It's C1
C1
plus XC2
C2x. Okay.
plus C3 e to the x
C3 e to the x. Good.
plus C4 cosine 2x.
Cosine 2x. There's no exponential here because there's no real part to that complex number. So it's just only the cosine part. Okay, good.
Plus C5 cosine 2x.
C5 sine 2x. Okay, good.
Plus C6x cosine 2x.
C6x cosine 2x. That's because it's a repeated root now. We put the x in front of it. Okay?
C7x sine 2x.
Hey, that's really good. It's perfect. That is the complementary function. Okay, I like it. Okay, so that's step 1. Now we have to work on the step 2, which is the annihilator part. Now, I didn't bring the table of annihilators with me here, so I'm just going to kind of hope that maybe you guys happen to have this one in your head already. Does anybody know how to annihilate 11e to the x?
Would that be d minus 1?
Yeah, that's just going to be d minus 1. It's pretty easy.
Yeah.
D minus 1. And does anybody know how to annihilate sine of 2x? So step 2 here.
Oh.
That's okay.
I forgot.
So d minus 1 was the annihilator of e to the x, and what about the sine of 2x? Anybody know it without the table?
Squared plus 4.
Yeah, it's d squared plus 4. You take 2 derivatives of sine, you get back to sine again, and there's a sign change. And the 2 keeps factoring out every time you take a derivative. So if you do it twice, you're going to have a factor of 4 out in front. So yeah, so it's just d squared plus 4. What do I do with these 2 annihilators?
The auxiliary? Or,
Say it again?
Multiply.
I multiply these annihilators, exactly, because even though there is a subtraction here, the original problem we have subtract 11 e to the x minus the sine of 2x, right? By subtracting these, but when you take annihilators, you have to multiply the individual annihilators. Okay, great. So this is what we're going to have. Perfect. So now we have to look at the new roots that we're getting here that we are now having to introduce. So what are my new roots?
1 and plus or minus 2i.
1 and plus or minus 2i, which actually are just repeats of roots we already got. So we have to keep that in mind when we're writing down the next terms of the solution. Okay, so before we go any further, remember I might only ask you for the form of the particular solution here. So if I only ask you for the form, then I'm just asking you to write down, without solving for the constants, what it would be. So can somebody tell me the form of the particular solution for this?
Ax e to the x.
Okay, great. So we have e to the x corresponds to the root 1, but we already had it earlier in the complementary function, so now I have to put an x in front of it.
Yeah.
And we have the a. Great. And then plus,
B,
okay, b,
x squared,
x squared,
cosine x, cosine 2x,
cosine 2x, very good.
plus c x squared sine 2x.
All right. These x squareds are because if you go back to the complementary function, you've already had 2 repeats of the cosine and sine terms, and this is now the 3rd time. So you're going to have those things showing up in it. So that would be the form of this thing. And certainly, looking at my notes, I didn't go any further because, well, I did do one more thing. I wrote down the final answer, which is y of x equals y sub c of x plus y sub p of x. Remember, this is the last step. Don't forget to do it. Step 3. The thing with this is that you would have to now, if you really wanted to find a, b, and c, you would have to take, what, up to 7 derivatives of this particular form? And you're already looking at nasty product rules right off the bat. It would be a nightmare to solve for a, b, and c. So I probably wouldn't ask you to do that. Yeah?
If it was like this on the exam, would we be able to write like y of x is y complement plus the particular?
Yeah, this is what I've been saying, is it's okay to do that as long as you've labeled these y sub p and y sub c. Again, if you're sloppy with your writing and you don't tell me what the complementary and the particular parts are, and I can't figure it, I'm going to guess wrong, right? If I don't see it on the paper, I'm going to probably guess wrong. So be sure that you're labeling these earlier pieces for me. Okay, so does that kind of make sense? Did you guys want to do one where we actually solve for the constants that's of the same nature, or is that kind of this hour of the night kind of boring and not that hard, or you can always read some on your own. I'm okay either way. There's a couple more things on. I mean, I've done almost everything here. I didn't do problem 8. And there's a couple of other parts of problem 6 that I didn't do. But I'd be happy to do another example or two, or I'd be happy to call it a day if people are not going to get anything out of it at this time. Information overload.
Can we do it?
Yeah.
Yeah, number 8. Oh yeah, yeah, absolutely. I'm happy to do number 8. So number 8 is, actually number 8 is a really good problem. Actually, number 8 is one I have used on an exam before, and I just moved it over to my review packet this time. So let's look at number 8. they give you a differential equation. I'm going to write this down first. The differential equation is x cubed times y triple prime plus x squared times y double prime minus 2x times y prime plus 2y equals 0. So they're giving you that equation. Now that is not a constant coefficient differential equation. In other words, in front of the derivatives, I don't just have numbers. If I just had numbers, then I would write down the auxiliary equation, find my roots, just like that problem. Right? This problem, if you expanded out the left side using the derivative notation that I see here, every single derivative would just have constants in front of it. This is not a constant coefficient differential equation. It does not fit into section 6.2 of the book, where we're covering that, where we do the repeated roots, complex roots, and all that stuff. So this is not one that I would expect you out of the blue to know how to solve, because we haven't talked about it. But I tell you in the question, find solutions of the form x to the r. So in other words, I'm sort of giving you what the look of the forms, the form of the solutions will be, and I basically want you to solve this for r. So this is kind of the form of the solution that you're looking for. It's homogeneous, by the way, so we're not going to be doing annihilators or variation of parameters or anything like that. We're just working on getting basically the step 1 part, the complementary function. And we're being told that this is the form that we can find those solutions in. It's not e to the rx this time. This is a different kind of differential equation that we have spent less time studying. So I'm going to give you a huge hint here and say, here's the form that you should be looking for. Right?
Yeah.
So what am I going to need to do?
Derive that 3 times.
Take the derivative 3 times so that I can plug it in up here. We actually did something like this a long time ago. So if I take the derivative, what is the derivative of x to the r?
Rx to the r minus 1.
R times x to the r minus 1, very good. And then the second derivative would be?
R times r minus 1 times x to the r minus 2.
Exactly. And then the third derivative here, r minus 1, and now we pull down the r minus 2 times x to the r minus 3. Okay, so I have all of that stuff. And we need to now plug these different derivatives into the various places that we see them up there. Okay? So, starting off with the top of the board there, I have x cubed times this thing right here, the triple derivative. So, r minus 1, r minus 2, x to the r minus 3. That's the y triple prime. And then plus x squared times the y double prime, which is r minus 1, x to the r minus 2. And then minus 2x, I'm just plugging into the top here, 2x y prime, which was r x to the r minus 1. And then plus 2y, which is just 2x to the r. All of that equals to 0. Okay, this is a key step here, is just plugging all of the derivatives into the formula. Okay, anybody see any way to make that look nicer?
The x cubed and the minus 3 on the exponent, they cancel out, leaving you just x to the r.
Okay, the first term really, when you multiply these powers of x together, it just gives you x to the r. Same thing here. Same thing here. And same thing here. We have actually x to the r in every single term. So what I'm going to recommend is that we just pull it completely out of every single term. So after we factor it out, I'm left with r minus 1, r minus 2, plus r minus 1, minus 2r plus 2 equals 0. Okay, great. So that's what we have. Now, I think I didn't write this down, but in the original problem, it says to solve the differential equation on 0 to infinity. When we write this down, this 0 to infinity interval, that's not telling you what r is. That's actually telling you what x is. That's the domain of the function that you're finding the solution for. So we're saying that x has to be greater than 0. It's in the positive interval. So if x is greater than 0, then you see, if I multiply it by this other expression and get 0, I know that this part is not 0. Right? So I can go ahead, and the part in brackets then has to be 0. I'm going to go ahead and erase here. I can always rewind the tape. You need to look back at what I have. These are just the derivatives. But I'm just going to take this part in brackets, which is r times r minus 1 times r minus 2, plus r times r minus 1, minus 2r plus 2, and set that equal to 0. This is my equation that's going to tell me what r is. Okay? The best way to expand this first term out is to kind of treat it as a FOIL of this part to get a quadratic, and then just tack an extra r onto everything. So I have r squared, but it's going to become r cubed. And then I have minus 3r, but it's going to become minus 3r squared, because there's another r here. The constant term is plus 2, so it's really 2r. Okay? And then the rest of it's pretty easy. We have r squared minus r minus 2r plus 2. All of that comes to 0. Right? All right, there should be some simplifying that we can do here. I see a 2r and a minus 2r. And then, let's see, the r cubed, of course, is here. R squared and a minus 3r squared is actually minus 2r squared. Okay, and then minus r and then plus 2 equals 0. So we're trying to solve this for r, right? We're trying to find the values of r that will make this work. Okay, so I'm going to go ahead and erase down here as well, just kind of sticking with the same board right now. Does anybody have a suggestion on factoring this thing? I want to group this thing into parts, right? So what could I group together? Like, how do I want to proceed?
Don't you do the first two and
Exactly. If I take just the first two alone and take as much as I can out of the first two. You see there's an r squared in both of these?
yeah.
So r squared leaves me with r here and minus 2 here. And then minus, I'm going to rewrite this last part as the quantity r minus 2. So I'm putting in parentheses to make that the quantity r minus 2 because I want to factor it with the other r minus 2. So you see, you're basically grouping things together and creating another common factor. Now you have what? R squared here minus 1 in front of this term times r minus 2 equals 0.
Your r values.
Okay, so what are my r values?
2 and plus or minus 1.
2 and plus or minus 1. Okay, no surprise, we got 3 r values. Now we're not done, because let's go back to the question here. The question said find solutions of the form and then determine the general solution. So we have found, how many solutions have we found here?
3.
3. And what are the solutions that we found? What are the solutions that we found
e
here?
to the 2x.
X squared, good, because there's an r equals 2 case.
X to, it's just x.
X by itself,
And x to the negative 1.
and x to the negative 1, like that. Exactly. So what would be the general solution?
C1 squared.
Whenever I say general solution, I'm always going to be wanting to see those constants coming up, right? So C1 times anybody?
X squared
X squared, good.
plus c2 times x
Plus C2 times X. Are you
plus.
catching this over here? I can't tell. I can see.
Oh yeah.
Okay,
Yeah.
sweet. So C1 times X squared plus C2 times X plus?
C3 times x to the minus 1.
Okay, there's the general solution built out of these 3 solutions. Now, what did I neglect to do here that I probably should have done with these 3 solutions that I put into the general solution? Yeah, I should check if they're linearly independent. And that's really because, notice that if you read the question, I asked for that. I said, find 3 linearly independent solutions and check linear independence. That's your clue
Oh yeah.
that I want you to check it. See, because this is not a standard problem where we always know that they are linearly independent. So we really should check it here. Okay, what's the tool that we use to check for linear independence? The Wronskian, exactly. So the Wronskian is what we need to do, the determinant, right? What size matrix am I going to have here? 3 by 3. And what do we put down the top row?
X squared, x, and x to the negative 1.
Great, x squared, x, and x to the negative 1. Okay, so then what do I do to get the rest of the matrix?
The derivatives.
I just take derivatives down the matrix. So the derivative of x squared would be 2x, and the derivative of that would be 2. The derivative of x would be 1, and the derivative of that would be 0. And then the last column, the derivative of x to the minus 1 would be negative x to the minus 2. And the derivative of negative x to the negative 2 would be 2x to the negative 3. Okay? So that's what we would have. And you could cofactor expand this, or you could just use the arrow method. I think is fine on this one. This is a 3 by 3. So I'm just going to use the arrow method. So I'm going to recopy the first 2 columns, like that, and just do my arrows. So here's one arrow here. This is x squared times 1 times 2x to the negative 3. That's just going to be 2 over x. Okay, using fractions now for that. And then this one is x times negative x to the negative 2 times 2. So that would be minus 2 over x. And then the next diagonal is plus 0. And then I go the other way, minus 2 over x, and then minus 0, and then minus, I think it's going to be 4 over x. Okay? Going kind of fast here, you guys can check that with me. But then when you simplify that, you're just going to get negative 6 over x. And the question you have to ask on the Wronskian is, can I choose an x that makes this non-zero?
Yes.
Pretty much anything will work, right? Just choose, you can evaluate it at anything in this interval from, forgot, the interval is 0 to infinity. Any x in that interval, so just pick x equal to 1 if you want. Just have to convince me that at least one value of x gives you a non-zero Wronskian. And that would do it. That would do it. Okay, so the set x squared, x, and x to the minus 1 is Li. They are linearly independent, and because it's a third order differential equation, we know that the dimension of this space is 3. I have 3 linearly independent solutions, so that's how I know that my general solution is the span of those 3.
Yeah.
They span the space. Make sense?
Yeah.
So the reason I like this problem is that the focus of this problem is not so much on just the procedural auxiliary equation stuff where you're finding roots and all that again. This is a little bit of a different problem where the focus is more on getting a solution to a differential equation that you're less familiar with. And you have to go back to the basic steps where you're checking the Wronskian and all of that. So I kind of like this problem as a diversion from all the other ones, which all seem to work the same. Okay? So that's kind of in, I would say this is in section 6.1 really. It's where this problem would be found. So, okay, I feel pretty good about that. We've done almost everything. There's a couple of problems on problem 6 that I didn't actually do. And of course there's other things I didn't really do. I didn't do a defective vector differential equation where you had to use the W3, W4, and W5 vector. You're working on that for the homework for tomorrow, for Friday. So you can take a look at that again, of course. And you know, there's going to be a few other things that have slipped through the cracks. Keep working at it. Really more than anything, guys, because I think a lot of you know the material pretty well. It's just a matter of, on the test day, actually getting those points, you know, not punting on problems completely, putting down, you know more than you think you know. And I'm not asking you guys questions that are completely out of left field. There might be a step or two where you say, gosh, I don't think I'm that comfortable with it all the time because maybe we didn't do it that much. But by and large, most of the stuff is going to be from the mainstream material. The things that I focused on the most, those are the things that I'm going to be asking you about and that you should expect most of the focus to be on. So be sure to get some good rest, and by starting early on the review, you're going to have that option. You're not going to be stressing out as much on Sunday night trying to get it all figured out. I think that's a good thing. All right, well, we've gone almost 3 hours. I think I'm going to call it good. Is that all right? Okay, sounds good. You want to